the last extra credit problem, there was a lot of text. And rather than just putting that up as a screenshot like I've been doing for all of the other problems in the exam, I want to take a little bit different approach here. So, in class we talked about a Fourier series of some function defined on some interval. We're going to take our interval to be symmetric from negative L to L. And I'll put a link to that video with the Fourier series in it. I'll put that in the description if you want to review that. But we said that certain functions, nice functions, that are defined on some interval, some finite interval, and there's more to it than that. But in our case, what we're talking about is functions that are defined on some interval, which you can make symmetric about the domain, so from negative L to L, or about 0, right? Then we could rewrite these functions as a sum of sines and cosines, where the a's are just constant numbers, constant real numbers, and the b's are constant real numbers. And what you get is something like this, right? A sum of sines and cosines. And we talked about how in order to find these coefficients, there's this nifty little formula here, right? An integral over the domain from negative L to L of the function that you care about times, for the case of your an's, times this cosine with n pi over L t, and ditto over here with sine for these. And the reason that that's true is if we're going to assume that this is true, that your function is indeed one of these guys. It can be written in this form. And so we have A0, A1, A0, A1 cosine stuff, B1 cosine stuff, or B1 sine stuff, A2 cosine stuff, B2 sine stuff, and so on, up to we get to the mth one, whatever that is. Maybe it's 15, maybe it's 700, and then plus the other mth one, and then so on, all the way up to infinity. These formulas work because of this fact. Let's say we want to find, let's just take a look at this. We take f. Here's your f of t, right? And if you multiply it through by cosine n pi L, that's the same thing as doing this. We take our f of t, multiply on one side by cosine n pi L t, right there. Well, when we do that, we do it to every single bit in the term, right? The cosine distributes over into each one of these, and we get cosine n pi L t. Here, we get another cosine n pi L t, and so on and so on and so forth. And then what we do is now we have this expression here, and we're going to integrate it from negative L to L. And so the integral, and then we have a dt. And the integral is a linear operator. So it's the same thing as integrating every one of these individually. So we do that. We integrate each one of these individually from negative L up to L. We integrate here from negative L up to L. And all infinitely many of them that we have. And we showed in that video that this, right? Well, first off, let's just take a look at this. Pull out the AM. And we go from negative L to L of cosine m pi L times t, cosine n pi over L t dt. And we showed that this always integrates to 0 unless n and m are the same number, right? So n and m, if they're the same, then this integral comes out to be L, right? And so if you then divide by 1 over L, each one of these gets divide by L, multiply by 1 over L. And that's the same thing as having a 1 over L here. And so then this works out to be L. And then your 1 over L kills that. You're left with the AM. What happens here? Well, sine and cosine, always, no matter what. Sine, this integral here, 1 over L bm, I'm just pulling out the bm and rewriting this integral here. Sine m pi L t cosine n pi L t. That always, always, always integrates to 0. So you get a big fat 0 here. And ditto with all of those others. The only time that it pulls it out is when m is equal to n, and then what you get out is that. So, in other words, you have some function that's a sum of a bunch of sines and cosines. If you multiply it through like this, and then integrate, then everything goes to 0 except the one where the m and the n are exactly the same. So, in other words, I could just rewrite this here. The only one that survives is the nth term. And that's how you could actually find a formula for this thing. So you do that. The only thing that's left, everybody's gone to 0 except for that one. The only thing that's left is the an 1 over L times L, which is what that integral works out to be. The L's cancel, and you get your an. That's how these formulas work there. But then I said that this right here is just a special case of what's really going on. I said that f of t is actually has this form right here. It's a sum of e to the I stuff with a cn, where these constants are actually complex constants here. And if we write this out real quick, let's expand this and think, okay, we have infinitely many things, and then we get to, let's say, the cnth one, and then we have e to the I n pi over L t plus cn plus 1 e to the I n plus 1 pi over L times t, and so on and so forth. And I said that if f of t is a real valued function, then this can be rewritten by monkeying around with these coefficients to be put in this form. And you can imagine how that could be, right? Because each one of these, we have Cn is some complex number, okay? This, we know from Euler's theorem, is the same thing as cosine n pi L times t plus I times sine n pi L t plus, now the next one is cn plus 1 times the same type of thing, right? We have a cosine plus I times sine. And I said, so basically, since each one of these are sines and cosines, you can imagine how you might be able to monkey this stuff around, and maybe something, you could rearrange it like this. But I said we didn't have time for that. And then in the actual exam, I put a ton of lines there showing that you might be able to go from one to the other, but then somewhere in there I said magic, math magic, and then everything kind of changes. But I just wanted to give you an example of how that might be done. Let's just do it. Let's just actually, I'm going to actually show you how we could get from here to here. Okay, so we're going to assume that our function looks like this. That there is a way of getting my function here to be written in this form right here. And then what I'm going to do is say, if f is a real valued function, then when we rearrange this stuff, it will indeed give us this right here. Okay, so let's do that. First thing we need to do is talk about complex valued functions. These are functions whose outputs are a complex number. And we're going to restrict our conversation to where the inputs, the variable that are going in, is a single real variable. You could have functions, complex valued functions, whose inputs are a complex variable, where you have some a plus I times b are the inputs, and the output itself is a complex value, right? You put in some complex number, do something to it, and out pops another complex number. That's cool, but that's not what we're talking about right now. We're talking about your input is a single real variable, and your output, you plug in a real variable into your function, and what pops out but some complex number, a plus, say, I, b. Okay? So you give me some t, I do some magic to it, out pops a complex number, a plus, I, b. Well, each one of these can be seen as actually two functions. This f of t can be seen as some real valued function, g of t, plus I times some other function, h of t, where h is a real value. Right? The outputs of h and the outputs of g are both real values. And then you have this I here. So, for instance, here's one that you know. Cosine t plus I times sine t, that's a complex number, and that function is e to the I t. There's my, call it g of t. So we've already seen something like this, we just haven't made it explicit. You plug in a real value, out pops a complex value. And here we can see it's the same thing as having two functions here. One function g, and one function h. But to make notation simpler, and actually let's just do one more. Well, because it doesn't have to be something crazy like e to the I stuff where we have this crazy theorem that we worked on. It took all year to kind of get there. This could be something very simple. We could say g of t is just, I don't know, how about 2it plus 3t minus 7i t squared plus, how about 2t squared? That's a function of a real variable t, and the output is a complex number. And what we can do is just rearrange this thing, get all of the real parts together. So we have 3t plus 2t squared. Okay. Actually, I'm going to rename this f for what I'm about to do. And then we just get all of the imaginary parts together. 2it minus 7it squared. And we could just rewrite this. 3t plus 2t squared is one of them. Pull out the I plus I times 2t minus 7t squared. And we can see this is the same thing as this is my g of t right here. And it is a pure real function, real input, real output, plus I times some other function that has a real input, and it will give you a real output, and we'll call that guy h of t. Okay? So, to make our notation for what we're about to do a little bit easier, instead of having an f with a g and an h, why don't we just say that the g of t, let's give it a new name, let's call it f with a little sub r for real. So that's the real part of f. And this part right here, can you guess what I'm about to write? F with a little subscript I for t, for the imaginary part. Okay? So you give me any complex valued function where you have a single real variable as an input, and believe it or not, we can rewrite it in this form as a sum of two real valued functions. Okay? Now we're going to do this. First, we're going to talk about complex conjugation. And the complex conjugate of any complex number, you could take this complex number, let's call this number c. That's just some complex number c. Its conjugate, we write a little bar over the top. The complex conjugate of it is simply, you just, wherever you see an I in the original formula, you make it a negative I. And so I make this negative I right there, B. And what that does is it makes that a minus IB, right? This, I'm sure we've done this before. So this should not be anything new. But one thing that might be new is this. Suppose you have two complex numbers, C times D, and we want to take that thing's conjugate. Okay. I claim that this is the same thing as taking the conjugate of C times the conjugate of D. That's my claim. And let's see if it's true. Okay. So let's take two complex numbers, C and D, and we'll say that D is, I don't know, D, how about E plus IF, where I and F are real numbers. And now what we want is we want to take CD, whatever that is, and then take its conjugate. So let's first off compute what CD is. CD would be A plus IB times E plus IF. We're going to multiply that out, and then we'll take its conjugate. Let's multiply it out. We get, okay, first outer, inner, last. AE, outer is I times AF, I times AF. Then the inner gives us I times BE, I times BE. And then the last one is IB times IF, which is the same thing as I squared BF. I squared is -1, so that should be minus BF right there. Now I'm just going to rearrange that. Oh, and then we're doing that, then we take the conjugate of it. And so let's get the real parts together. We have AE minus BF. The I can be pulled out of that, leaving me with an AF plus BE. Then I take the conjugate, and by definition, the conjugate, we just, wherever we see an I, we make it negative. So let's just make the I negative, and that has the result of going AE minus BF minus, instead of plus, now we have a minus I AF plus BE. So that's what I get when I multiply it out, then take a conjugate. I'm just going to rewrite that right here. So multiply out two complex numbers, then take a conjugate, and I get this, AE minus BF minus I times AF plus BE. Now, the question is that the same thing that I would get? Is this the same thing I would get as if I took the conjugate of them first, C conjugate, D conjugate, and then multiplied it? Let's find out. C conjugate times D conjugate is the same thing as the conjugate of C, which is A minus IB, times the conjugate of D, which is E minus IF. E minus IF. So now first outer, inner, last. Let's see what I get. AE is AE. Outer is minus AIF, or IAF. Inner is minus IBE. Now we have a negative IB times negative IF. That's negative I times negative I times negative IBF. Negative I, negative, well, negative, it doesn't matter where we are, negative times a negative is a positive. So that's I times I, BF. So that's negative 1 BF, or we'll just write it as negative BF. Rearrange these guys. This is the same thing as AE minus BF minus IAF minus IBE. Pull out the minus I get AE minus BF minus I times AF plus, because I pulled out a negative in both cases, the minus came out, so that gives me a plus BE. Is that the same thing as doing it that way? Yes, okay. So that's what I wanted to show, right? That when it comes to complex numbers, if I have two complex numbers, multiply them together, and then take the conjugate, it's the same thing as if I took the conjugates of each and then multiplied them together. One more thing before we move on, just one more thing to say, is that if you have something of this form, e to the e to the, say, ix, and we take its conjugate, like I said, conjugate, you just, every time you see an I, you just make it negative. And so I claim that that's the same thing as that, right there, right? Let's just make sure, that's what I'm saying, is that if you want to take the conjugate of e to the I something, you simply make that negative. Is that true? Let's find out. So e to the ix is the same thing as cosine x plus I sine x. If I take the conjugate of that, well, I make the I negative, and so it's negative, like that. But that's the same thing as cosine x plus I sine negative x, right? And cosine, because sine is odd, right? Sine is an odd function. So if the negative sign is the same thing as positive, putting the negative inside, right? Cosine's an even function. So I could make the inside negative and it doesn't change anything. Right? Cosine of negative x is the same thing as cosine positive x. It's an even function. Sine's an odd function. And so negative, here I am. Negative sine x is the same thing as sine of negative x. And so this, just by definition, is the same thing as e to the I negative x, which is the same thing as e to the negative I x. And so yes, it does work. You want the conjugate of e to the I stuff, simply make the I negative. And that works no matter how crazy your function is, right? Like the square root of 2i plus 3 sine it. If you want the conjugate of that, you simply go through and make every I negative. It just works, okay? Just trust me on that. We have a complex valued function. And we could take its conjugate, because the output here, remember this just represents the output. You chose some t, say 5, you plug it in and out pops some complex number, right? Maybe you plugged in a 5 and you got a 2 here, and you plugged in a 5 and you got out a 3 here. Okay? So we could take its complex conjugate, and that would be 2 minus I times 3, right there, right? And so we could do that with every single output of this thing, and we could do that by just taking the conjugate, and we would write it like this. We would take the conjugate of the output of this function, and that's the same thing as just whatever your function would have been, but you just make the I negative, just like this. I, t. Boom, easy. Now we can do something cool. Same way when we were deriving a bunch of formulas from Euler's theorem, we could just take these two things and add them together. And watch what happens when we do that. On the left-hand side, we get f of t plus the conjugate of f of t equals, well, look at this. This is exactly the same thing as this, it's just negative. So when you add them together, you get a big fat 0. Here, you have the same exact thing over again, so it's just 2, real part, f. Big fat 0, not even going to bother writing it. Now, watch this. The real part of f is the same thing as the average of the function, the original function, with its conjugate. And so if you give me any complex valued function, I could get its real part by adding it with its conjugate and dividing by 2, or taking the average of the function itself with its conjugate, and I get just purely the real part. If I want to obtain just the imaginary part, I could do a similar thing where I just take this function, take its conjugate, and I'll just subtract off the conjugate. So I have, on the left-hand side, f of t minus the conjugate of f, and that's, well, this minus this is a big fat 0. This minus a negative is the same thing as plus a positive. So I'm going to get 2 of them. This would be plus 2i f, imaginary part, t. And then I could solve this, and I'll get what's over here, f of t minus f conjugate of t. If I divide by 2i right here, then I get a purely real function. This is, because remember, the only imaginary part in this is that I. Everything else there is a purely real function. And so I get another real function, like this. And how do we know it's real? Well, look at this, right? What you've just obtained was something, and all of the i's were out here. There's no real part over here. All of the i's are out front. 2 of them, actually, 2 i's out front. So if you divide off that 2i, the only thing you're left with is the real part right here. And confusingly, that's the imaginary part, the imaginary component of our original complex valued function. Before we move on and tackle this guy, let's just remember that every real number, right, here I've drawn the complex plane, here's the real line, and here's the imaginary line, or the real axis and the imaginary axis. Every real number is a complex number, right? They are a subset of the complex numbers. You might say 5 doesn't have an imaginary part. Well, it does. 5 itself is 5 plus I times 0, right? Like 5 plus 2i, obviously, is in the complex plane. 5 minus 2i is obviously in the complex plane, but so is 5. 5 itself, like all the real numbers, are complex numbers. It just so happens to be that their imaginary component is 0. Similarly, all real valued functions, that's functions whose outputs are purely real, can be written like that, right? Its real component is whatever it is, and its imaginary component is just constantly 0. Okay, just keep that in mind. Keep that in mind. That's going to come up in just a second. Now, okay, let's suppose we have a function. And let's suppose that it's one of those functions that can indeed be written like this. Okay, so this is, I've just expanded this thing right here. We have f of t. N goes from negative infinity up to infinity, Cn e to the I, pi n L t. Right? That formula that I had on the board a minute ago, right? Where each of the c's are complex numbers. Okay, and n goes from negative infinity to infinity. And so, if we start here at 0, or n equals 0, and work our way towards positive infinity, we get c1, c2, and so on, all the way up to cn, and it continues. And then going in the other direction, we get negative 1, c negative 2, and so on and so on, c negative n, and so on and so on and so on. And all I've done here is I've just written some representational one, or some choice ones here, and I'm just letting n go from, in this case, we're going from negative infinity up to negative n, and we see we have a negative n right there, and so on. Then we get, finally we get up to negative 2, and there's a negative 2 up there where the n is. When n is -1, we have a -1 right there. When it's 0, we have a 0. When it's 1, we have a 1. When it's 2, we have a 2. When it's all the way up to n, we have an n. One thing I want to do just to simplify things a little bit is notice that since I have a 0 there, I pi times 0 over L times t is what's in that right there. That's that guy. Well, the 0 makes all of this go to 0, right? 0 times pi is 0. Over L is still 0. Times t is still 0. And then I times 0, that's just a big fat e to the 0, and e to the 0 is 1. If you don't like that, you could say e to the I times 0 is cosine 0 plus I times sine 0. Sine 0 is 0, cosine 0 is 1. Okay, so yeah, that's good. So what I'm gonna go ahead, just for ease of what we're doing here, I'm gonna rewrite that as e to the 0, and then go ahead and just say, well, that's just equal to 1. So let's just get rid of it. We'll get rid of that. So all that's left is just the c0. Okay, so we have some function. It might be real. It might be a real valued function. Okay? But we're writing it in complex terms here. All of these c's are complex numbers. And obviously the e's of the I stuff are complex numbers. But what we could do, and regardless of whether or not it's real, we could say, well, let's take f, add it to its conjugate, divide by 2, and that will give me just the real part of f. We know that that's the case, right? We could do this similarly with whatever. But if indeed f itself were a real function, like let's do this with actually something here. F of t is just t squared. It's purely real, but we're imagining that there's an imaginary part there, that it just happens to be 0. Well, then what do we get? Well, f is t squared plus I times 0, plus the conjugate would be t squared minus I times 0, divided by 2. Well, I guess that would be t squared, I guess just 2t squared, 2t squareds, divided by 2, and we just get t squared, which, if that's the case, then the real part of it is indeed the whole thing, right? There's nothing magic going on here. If your original function happened to be a real function to begin with, then when you do this, you just get back what you started with, obviously. Okay, so just keep that in mind. Yeah. Everything we're about to do will still work whether or not f is real, purely real, or if it has a complex part. But if it is purely real, then what you get back is going to be the actual function itself. So that's what I'm going to do here, okay? I want to take the conjugate of f and see what I get. Okay, well, the conjugate, and actually we didn't do this one earlier, is that the conjugate of a sum is the sum of the conjugates. Is that true? Let's just make sure. I do want to make sure that we're getting this right. So if C is A plus IB, and D is E plus IF, and I want to take its conjugate. My claim is that I could add these together first and then take the conjugate, so let's do it that way. So A plus E plus IB, IF is the same thing as I times B plus F, and then we take its conjugate. So that's the same thing as A plus E minus I B plus F, right there. Now, is that the same thing as if I had done it the other way around? So let's see, is that equal to, take C and its conjugate, add it to D and its conjugate. Here we have that C was A plus IB, D was E plus IF. Okay, so we're going to do the conjugates first, then add them together. So take the conjugate first, A minus IB. Add that to what? The conjugate of this, which is E minus IF. And then grouping these guys together, we get A plus E as the real part. minus IB minus IF is the same thing as minus I times B plus F. And let's just check that. The minus I comes in and gives me the minus IB. Minus I comes in and gives me the minus IF. Yep. So they are the same thing. So in other words, I want to take the conjugate, and then we could extend this, because what if C itself was a sum of something? Well, it would still apply, right? So that C plus D conjugate is the same thing as C plus D, but if C itself were a Z plus W, then this would be a Z plus W right there. But by what we just proved, that's the same thing as Z bar, W bar, D bar, right? So this just extends. In other words, we could do this to the whole thing. Taking the conjugate of every single one of these complex numbers is the same thing as just taking the conjugate of each of them, okay? And so I'm going to do that here with this first term, which is C negative n e to the I pi negative n over LT. And I'm going to take its conjugate. But as we've already seen, that's the same thing as taking the conjugate of C and then multiplying that by the conjugate of I negative n LT, like that. The conjugate of this is whatever it is. I don't know, C bar, negative n, whatever that complex number is. Maybe it was 3 plus 2i. I take its conjugate, well then it's just going to be 3 minus 2i. That's what that's going to be, okay? But whatever it is what it is. And now, like we just said, C negative n bar, and that's how we say it, bar. That's the same thing like we just showed. E to that stuff is, well, you just make the I negative. It's that simple. You just make the I negative, and now we have pi negative n over LT, like that. Oh, but wait, that's a negative and a negative, right? That's just I times all that stuff. In fact, I could even write it as negative I times pi times negative n all over L times t. And that's a negative and a negative, it just makes it positive. Right? So that's the same thing as C negative n, whatever that complex number happens to be, take its conjugate. Now, instead of the negatives, I could rewrite that as I pi positive n over LT, like that. Okay, so that gives us the first of our infinitely many things we have. That's the conjugate, negative n, e to the, now it's just positive I pi n L t. Plus, and we do that with all of these. Finally, we approach negative 2. And I'll take its conjugate. The conjugate of the whole thing is the conjugate of each one of these individually. The conjugate of that. And again, now we're going to have a negative I here and a negative 2. When I take its conjugate, we'll have negative I pi negative 2. Well, that's the same thing as just positive I pi positive 2. Right? So I'm going to rewrite that as e to the I pi times 2 over LT. This one is the conjugate of whatever that is. And then this is just positive, I pi 1 LT. The conjugate of C0, whatever it is, plus the conjugate of C1, E. Now that's negative I pi 1 LT plus the conjugate of C2, whatever it happens to be, e to the negative I pi times 2 LT. And so on, all the way up to Cn, take its conjugate, and then take the conjugate of this, which makes that negative I pi n LT, and so on. Now I'm going to add these things together, because I am on my way to getting just purely the real part. That's what I want. That's what I'm interested in right now. I'm going to add these guys together, and then I will be dividing them by 2 eventually. And we know that what that does is gives me just the real part of f. Because like I said, the whole thing we're trying to prove, right, was that this thing can, if it's real, can be rewritten in just the terms of the sines and the cosines with no i's whatsoever. So if it's real, then when I do this, I'm going to end up with the original function. Okay. What I'm about to do will still work if it's complex. It's just, it just won't, you won't have a purely real function, but that's no big deal. So we have f of t plus the conjugate. Now let's see if we can make this a little bit simpler here. I notice right away that, and actually I'm going to start with this, there's no e's in the c and the c0. Okay, the c0 and the other one. So c0 plus its conjugate right here. Right, I'm just going to put that together. Now I notice something interesting. Over here, all of these guys were positive, right? I times pi over 2, 2 pi over 2, n pi over, oh, that's not over 2, that's an L. I'm sorry. So that's exactly the same thing going back down here in this direction, right? That this I pi times 1 over LT is the same thing as this I pi 1 LT. The 2 pi 2 L, here's a pi 2 L. So as we go out this way, right, this one's the same as this one, this one's the same as this one, and so on and so on. And finally, look, yeah, look at that. That one's the same as that one. Okay, so I'm gonna group those together and say, so look at what I'm doing here. I'm saying that C1 e to the I pi times 1 over LT. If I take that and add that to this one, C1 bar e to the I pi 1 LT. It's the same thing. Since it has the same term there, I could pull it out. What do I get? C1 plus C1 bar e to the I pi times 1 over LT. So let's put that up here. Okay, so we have C1 plus its conjugate, C1 bar, like that. And then this guy right here, e to the I pi times 1 over LT, like that. Okay. Let's move our way out. Oh, but now look at this. I'm going to go ahead and get this one. These guys have the negatives, right? That's the same thing as this. Just to be explicit here. C negative 1 e to the pi negative 1 LT. If I add that to this one, C... look at what I did. I added that one and that one to get that. But that's a negative 1 bar. Negative 1 right there. Right? Oops. Ow. Sorry. Negative 1. Because I got that one by adding this one and this one. That was C1 and then C negative 1 bar. You cannot guarantee that they're the same thing. Right? But we can't guarantee that any of these coefficients are the same as any of the others. In fact, we're going to go ahead and assume that they're all entirely unique. We have no way of knowing that this one's the same as that. In fact, they're probably not. I'm going to go out on a limb and say this one and that one are not the same thing. This one and that one, they're not the same thing. We can't assume that. So we have to be very careful with these negatives here. Okay. Okay. So I grabbed this one here. Uh-oh. Oh. C negative. I grabbed this one here with the negative 1. The other one that had a negative 1 up here was C positive 1 bar e to the negative I pi times 1 over LT, like that. You see why I didn't bother doing this in class or writing all of this up on in the exam? This is no laughing matter here, okay? But we notice that these are the same, right? Pi, oh, I didn't put an I there, sorry about that. But that's the same thing. I could pull this negative all the way out and it's the same thing. And so what we get is C negative 1 plus C positive positive 1 bar. And what pops out is negative 1 pi times 1 LT, like that. Okay, so the next term here is going to be C negative 1 plus C positive 1 bar e to the negative I pi 1 over LT, like that. Okay? I'm not going to bother doing the 2's, but you'll get the same thing, right? Here you have a positive 2 and a positive 2, so we'll put those together. We have a negative 2 and a negative 2, we'll put those together, and we keep doing that on and on and on and on and on. And now finally, I do want to get these last ones out here, okay? So we have the positive Cn and the negative Cn bar. We have C negative n bar e to the I pi n LT. We add that one to this one, which is plus Cn e to the I pi n over LT, like that. Those are the same, so I could pull them out. We get C negative n bar plus Cn e to the I pi n over LT, like that. So C negative n bar Cn e to the I pi n LT. Then we do that with the other one, right? I'm messing. I was just going to like write a couple things and modify that. I'll mess it up if I do that. Let's do C negative n e to the, that negative n up there could come out as negative, like that, pi n LT. This one plus C positive n bar gives us E, same exact thing right there, LT. So I could pull him out. And I'll get C negative n plus C bar positive n e to the negative I pi n over LT, like that. So C negative n plus C positive n bar e to the negative I pi n over LT, and so on. You can't say I'm putting the and so on and so on. It goes on forever, right? Here's where we have to be really, really careful. Because, like I said a minute ago, now you'll notice I got rid of the ones and the negative ones and stuff like that. Because we don't really need any of them. In fact, this n is arbitrary. We could replace that with any integer you want. You want to know about when there's a 5 up there, we'll just plug in a 5 there, right? 6 right there, plug in a 6 there, and it's all going to work. I left this one here because there's something fundamentally different about this term versus all of these other terms. And that's that we can guarantee that the C0 term is the same thing. We can't guarantee that the Cn is the same as the C negative n. You know what I'm saying? And so, because each of these, there's no guarantee that this guy is in any way related to this guy, right? C1 might be 3 plus I 2, and C negative 1 might be 7 minus I don't know, times pi. We can't guarantee that these guys are related, but the C0 is the exact same thing. These are related. And so they show up in the same term. We could go ahead and just deal with this. Please stop that, guys. So let's rewrite C0 as some, I don't know, A plus I B, where A and B are real numbers. Okay? Well, then its conjugate, C bar 0, is just A minus I B. So when we take them and add them together, we get C0 plus C0 bar, which is that term right there, that term that we're looking for. Well, the imaginary part is gone. This is a purely real number. And it's 2 times whatever that original component was. Okay? So I'm just going to go ahead and just call it 2a. For some a. We don't know what that a is. Okay, so that's 2a. Right there. Now here's where we had to be really, really careful. I want to rewrite each of these terms in components, right? We know that Cn is a complex number, so I'm going to go ahead and do this here. Cn is some complex number. Let's call it capital A-N plus I times capital B-N. Again, there's no guarantee that that's actually a positive number, right? A-N might be 3.1 and B-N might be negative 7.2, in which case this is 3.1 minus I 7.2, right? And then Cn bar would then have to be An minus whatever that is. And if that's the case, then we'd make the minus a minus, and that would be a positive, right? At any rate, they have opposite signs here and here, right? But those aren't added together. It's negative n, and this is why we have to be so careful here, is that the C negative n, how do I want to write this? Let's do it this way. Let's do it this way. I'm going to rewrite that guy right here. Cn bar is whatever An is minus Ibn. Okay? Now really carefully, we're going to say, okay, what about C negative n? C negative n? Well, it can't, it's not necessarily the same thing as An, but we could call it A negative n, as long as we remember that this negative n means that these things are not necessarily the same. They might be the same, but it could be the case that An was 0.02 and A negative n is 3.4. Right? Just keep in mind that these are not the same, so we can't just make simple assumptions that, oh, they're going to cancel out or something like that. We don't know that. We don't know that. That's why I'm taking pains to write my subscripts with the negatives there. Okay? So, okay. Forget that he's there. Don't get caught off guard by that. Cn, we're going to say it's not a conjugate, so we're going to go plus I, whatever B negative n is. Okay? And its conjugate is then what I get when I make the I negative. So the conjugate C negative n bar, right, is A negative n minus I B negative n. Okay, so now we're ready. Okay, we could rewrite this coefficient right here. Let's do this one here. Cn, there's Cn, C negative n bar, C negative n bar, that thing is what I get when I add these together. So let's add them together. Cn plus C negative n bar. And what do we get? Well, I guess An plus A negative n plus I times, I could rewrite that as Bn minus B negative n, like that. Right? Did I do that right? We have I and I, yeah, the Bn would be positive. That, pull that out. Yeah, okay, that's good. That looks good. And so over here, when I add those together, guys, please keep it down. Please. We'll fill that in a second. Now this guy right here, we have C negative n, there's C negative n, C positive n bar, C positive n bar. We're adding those together, and what do we get? Cn bar. I'm going to do it in the right order here. C negative n plus C positive n bar is the same thing as, okay, An, A negative n. And then bn, how about plus I, and we'll do the b negative n first, minus b positive n. Like that. Yeah? Okay. So let's go ahead and replace these. So this is the same thing as, let's use brackets. A n plus a negative n plus I times b n minus b negative n, all times e to the I pi n L t. This next one, big bracket, that was this one, yes. So we have a n, a negative n, plus I times b negative n minus b n. And that was that one. E to the minus I pi n L t. And all the other ones going on out forever. Okay, we're almost there. Let's recall one nifty fact. So, e to the I x is cosine x plus I sine x. E to the negative I x is cosine x minus I sine x. And so, if I add these two things together, I get e to the ix plus e to the minus ix is the same thing as these guys cancel, and I get 2 cosine x. Okay. Okay. And if I that's when I add them together. When I subtract them from each other, e to the ix, e to the minus ix, here's my cosine x plus I sine x. Here's my cosine x minus I sine x. And when I subtract them, e to the ix minus e to the minus ix. That's the same thing as 2I sine x, like that. Okay? Now what I notice here is in each one of these terms, that thing's the same thing as that thing. And so now I'm going to go through this entire sum and regroup all of these things so that I'm going to get all of the a-n's together. And I'm going to try to do this one, leaving this right here. Let's not forget that. So this is the same thing as 2a, all of these. Now let's look at this. A n, a negative n. E to the I pi n over lt. This guy comes in as I bn minus b negative n e to the I pi n over lt. Okay, I just distributed him into there. Distributing him into here, we get a n, a negative n, e to the negative I. Please keep it down. Now, plus I times b negative n minus b positive n e to the minus I pi n over lt, like that, and so on. Now, because I know this nifty fact, that's going to motivate me to go, whoa, 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 wait a minute. This is the same thing, right? In fact, pretend he's not there. We could pull the n plus a negative n out of there, can't we? And what would be left? Let's see. Hold on. 2a plus, and so on, again, I'm going to take this one and pull out the an plus a negative n right there. And what's left over? Well, it would be this plus this, which is e to the I pi n over lt. And then this one is plus e to the negative I of the same stuff. Like that. Now, these two are together, right? But that's not the same thing as that, is it? Right? This one is b positive n minus b negative n. This one's b negative n minus b positive n. So I'm motivated by looking at this thing here and saying, you know what? You know what I'm going to do? I'm going to pull a negative out of this. Make that negative I, negative b negative n plus bn right there. Now we can see that's the same thing as that, right? To be really explicit, that's the same thing as minus I bn minus b negative n, right? Check that, that is the same thing as that right there. So I'm going to go ahead and do that. I'm going to rewrite this. I'm going to rewrite this as that. I'm going to say that's the same thing as minus I b positive n minus b negative n, like that. And now we have that and that are the same number. And so forgetting about him right here, I could pull out that bn minus b negative n from both of these, and with the I, I'm sorry, wait, yep, with the I, okay? So I'm going to pull out all of that, and what pops out is the I bn minus b negative n, and what's left over is this plus this. I'm sorry, this minus this, yeah? E to the I pi n over L minus e to the negative I pi n over L. Like that, and all these others. Let's just double check that. Let's double check that I did that the right way. If I multiplied this back into here, I would have this times this, which is right there, and then this times this, which is right there. This thing being multiplied back in, boom, multiply him into here, and we would get this guy back, yes. This back into here would give me a negative I bn minus b negative n, yes, times this thing, which is right there. Aha. Now, here we go. Look at this. E to the I stuff plus e to the minus I same stuff, which is exactly what we have here, is the same thing as 2 times cosine of the stuff without an I in it. So this, I have 2a plus, whatever this is, an plus a negative n, some number, some real number, right? That's a real number because the a's, remember, this came from Cn, which we said was an plus I bn, right? And both the an's and the bn's were real numbers. The only imaginary thing was the I there, which is no longer here. So that's a pure real number right there, times this thing, which is 2 times cosine of whatever this stuff is. In our case, pi n over lt, right there. Now what's left over here? Well, we have our plus I bn minus bn. Again, this is just a pure real number. The b's are purely real. So this is some real number, bn minus b negative n times this right here. And what is this? Well, this is e to the I stuff, minus e to the negative I same stuff, minus e to the negative I same stuff. So this right here is the same thing as 2 times I times sine to that stuff without the I in it. So this is 2 times I times sine of the stuff without the I, which is pi n L t, like that. Okay, now this I times this I. Remember, this is all, now this forget about him. This is some real number. 2 is some real number. Sine of a bunch of real numbers is a real number. So this is just I times some number, call it k, times 2 times I times sine of some other stuff, which is some other real number, call it L. Okay, that's the same thing as I squared times 2 times k times L. I squared is just a -1. So I'm going to take this I here, this I here, put them together as I squared and make it negative. Okay, so what do we have? Equals 2 some A plus a n plus a negative n times 2 cosine n pi L t. The i's make that a negative, so that's negative b n b negative n. The 2 is there. Actually, I would like to take this 2 from over here and pull him out front. Let me rewrite this. Let me rewrite this. I want to reason this through. Oh, and I didn't do my ellipsis. Oh, that was bad. Okay, so 2a all the way up until we get to here. So there's some real number, a n plus a negative n, whatever it happens to be. There's a 2. I could rewrite that as 2 times that stuff, a n plus a negative n, times the cosine stuff. Cosine pi n L t, like that. I said that the I and the I is the same thing as a -1, so I'm going to write that as minus. The bn and the b negative n is just some real number. Don't care what it is. But it's a real number, because the I is gone now. The 2 comes out, boop, like that. I'm just going to put them out front. So now let's take a step back and look at this thing. Okay? We said that you take your function, add it to its conjugate, and what you get, as we expected, is a pure, real number, right? All of the i's are gone, aren't they? Right? And what's left? Well, we have 2, in every case we have a 2, and that's what I said we were going to do at the end, right? Like here at the very end, we're going to say, well, hold up. If I divide this thing here by 2, divide all that by 2, divide all that by 2. Well, there's a 2 in every single term, isn't there? So I divide every term out by 2, and what we're left with is some a, why don't we call it a 0, because it came from the 0th term. Okay? Do the same thing with the 1 and the 2 and the 3, all the way until we get out to the nth one. The 2 is now gone. And why don't I rename this? Instead of capital A n, why don't I rename it lowercase a n? Because that's just some real number. That's some other real number. Add them together, it's some real number. And it's the nth one, right? Because we took the negatives and the positives and combined them in both of these cases. And in every case, right, they did this. They gave us that. So the nth one, we'll just call that an cosine n pi L t. Now this, it's a minus, yeah. Get rid of the 2 because we divide it out by the 2. We don't have to write it as minus because we don't know whether this thing is positive or negative. And so I'm going to say, well, whatever this number happens to be, there's my real number, bn. And I'm going to subtract off some other real number, b negative n, whatever it happens to be. It might be 5 and 7. It might be 403. So we don't know whether or not it's positive or negative, but in any case, whatever it works out to be, it's some real number. Let's just call that real number lowercase b, n. And we'll like make it, we'll say negative, I don't know, whatever, who cares? It'll look a lot better if we just say plus. Because we don't know whether it's positive or negative to begin with. So this thing is then plus bn sine pi times n over L times t, and so on for all of those. So what do we have here? This is exactly the same thing. So if your original function did start off, if your original function is indeed a real number, a real valued function, then what you do when you do this, you get your original function back. And so that's what I said, that what's really going on is we assume that the function looks like this. And if it happens to be the case that that's a real function, it can be rewritten like this. In fact, I'm going to go ahead and do that right here and say this function that we just wrote out, when you do this to it, it is the same thing as this, as we just showed. A n cosine n pi lt plus b in sine n pi lt, and so on. Okay? And so this thing right here is the real part of your original function, using our notation that we introduced earlier. If you want, you could then go through the same way we did and get f of t, but now go minus f conjugate, f bar of t, divide by 2I, and when you do that, all of these things are going to work out to give you a pure, real function. And it'll be the imaginary part, right there. That'll be the imaginary part of your real thing. And then you could put them back together if you're so inclined to get your f of t is equal to your real part that you got this way, right there, that sum. Add that to I times your imaginary part that you obtain doing the same thing, but instead of subtracting them off, and it's almost exactly the same. There's just a minus somewhere else, and you have to keep track of that. Divide through by 2I, it makes all the i's go away, and all of those 2's go away. It's another series, but there you go. But if it's the case that your original function was a pure real function to begin with, then this thing works out to be a big fat 0, and what you have is that your original function, which was real to begin with, is indeed this thing right there. And so you could drop the r and say, yes, since my function was real to begin with, we knew it was real, then this is the same thing as this right there. It turns out to be much more useful to think about this thing, whether or not f is a real valued function or a complex valued function, to think about it in these terms here, to pretend that it is a complex valued function, even if it's real, when you're actually doing this. Like, yes, we just went through all of that and showed that, yeah, if it's real, then the function is the same thing as the sines and the cosines, and that's great. But it turns out to be much more useful to think about it like this. And let me show you why. If f is indeed a sum of a bunch of these things, right? So it's a bunch of these, and let's give it some name. Let's just say that there's the mth one right here, right? And so what does that look like? Well, I guess I times pi m l t, like that. Okay. Now, if that's the case, remember we had these formulas. In order to get a n, the nth one, we integrated, divide by L, from negative L to L of the original function times the cosine part. And that made everything pop out, right? It killed everybody that was in this sum except for the one that, for which the cosine matched up, right? We could do a similar trick here, and instead of using two different formulas, one for the A's and one for the B's, we could right now derive a formula for just getting the one that we care about, okay? With one integral, and that's kind of nice. And what we're going to do is, big surprise here, we're going to multiply this entire thing by the conjugate of the one we care about. So I want my Cn here. Okay, I want to find whatever the Cn is here. And you could kind of imagine if you took this thing and multiplied every one of these through by the conjugate of whatever this is, which would be minus I pi n L t. You multiply every single one of these through. This thing, when you multiply it right here, what's going to happen? Well, you're going to have your Cn e to the positive I pi n over Lt. Multiply these two things together, it's the same thing as e to the I pi n Lt minus I pi n Lt. This is just a big fat zero, and all you're left with is just a Cn. But simply multiplying the whole thing across isn't going to kill all of those, unless all of these other ones, right? You'll get your 1 right here. That'll be a 1. But all of the others aren't going to be 1. How do you get rid of them? Well, you integrate against this. Right? The same way that we did with the sines and the cosines. That is explicitly what I'm going to do is I'm going to take my f of t, whatever it happens to be. It looks like this. Here's one of these many things that are there. And I'm going to multiply it by the one that I care about, the conjugate of the one that I care about. Which in this case, let's say I'm searching for Cn. That's the constant that I want. Well, I'm going to multiply through, first thing, by e to the minus I pi n over Lt. And so I do that to every single one of these that's in the term, or all of these terms, and I get minus I pi n Lt. Now let's see what that thing is. Okay, so we have a Cm. This and this we could rewrite thanks to Euler's. Oops, I'm gonna give myself a bit more room here. Thanks to Euler's theorem, we could rewrite this as cosine n mLt plus I sine, pi m Lt, pi m over Lt here. This one is cosine pi n over Lt minus I sine pi n Lt right there. Okay, so that's what happens when I just multiply it through. I'm going to simplify this up a little bit. And remember, that's for every single one of these. This has just happened to it. We've just multiplied it through, and now it looks like this for every single one of them. I could say, okay, well, what do we get here? Well, it's Cm. That hasn't changed. Now, first, outer, inner, last. We're going to get a cosine, cosine. So I'm going to be lazy here. Cosine, cosine. Minus I cosine sine. I'm going to be lazy, but I'm going to keep track of what this came from. There was an m in this one, and there was an n in this one. There was a m in this one, and there was an n in this one. Now we have a plus I sine m cosine n minus I squared is the same thing as plus 1, right? Because that's minus negative 1. So that's plus 1. So I'm just going to write that as plus sine m sine n. And I'm just being lazy by not writing out everything that's in there. That's actually a pi m over lt. Pi n over lt, but I'm just doing that, right? Okay, now, this is the big payoff here. Because now when I integrate this guy from negative L to L, so that's what I'm going to do. I'm going to integrate this thing from negative L to L. So I integrate every single one of these terms, right? Every single one. And that's the same as doing this, which is the same as doing this. And now that's doing this right here from negative L to L. I could pull out the constant. I get Cm from negative L to L. And now this thing, instead of writing all that, I'm just going to integrate each one of these individually. We have my cosine minus I times the integral cosine sine plus I times the integral sine cosine plus integral negative L to L sine like that. And like we already said, doing this over a symmetric interval, cosine sine always goes to 0. Sine cosine always goes to 0. Cosine over this interval it will always be 0 unless these two things are equal, right? The only way to get cosine pi m over L times t and cosine pi n over LT, they will always be 0 unless n and m are the same thing. Okay? And so if the n that you chose was equal to n or whatever, then this thing right here will work out to be just a big fat L. So we have Cm times L plus a 0, and ditto right here. As long as n and m are the same number, it will go to L. Otherwise, if m and n are different numbers, then it'll go to 0. So all of these other terms are 0, all the other terms are 0, and as long as n and m are the same number, then you will get this right here. So let's go ahead and rewrite that right here. Getting that's equal to Cm times L plus L, which is the same thing as Cm times 2L, right there. And if the thing you were trying to find in the beginning, and again, that m, that's only going to be the case if m is equal to n, so why don't I just go ahead and rename it n right there, right? Otherwise it would have disappeared. So there's my Cn is the only one that survives. When I choose an n here, the only one that's going to survive is if that one is the same as that. So if that's my original n right there. All the other ones are going to disappear, which is really nice, right? And so now we end up with this nifty little formula. That integrating from negative L to L of your original function times e to the minus I pi n over L t dt gives you the coefficient that you're looking for, Cn but times 2L. And so we divide both sides by 2L to get this. Slightly different, right? We had the 1L in the case where you've split them up, right? But as we just saw when we derived this, they're not split up here, right? You get your part from the sine, from the cosine, and your part from the sine, and so you end up with 2 times as much, and that's why you need to divide off by that much, right? So, okay, nifty. So, right, doing this to some function, any function, will give you the coefficient right here. And as we said, these coefficients correspond to a given frequency, right? And what do we mean by that, right? Like this corresponds to e to the I n pi over L t, right here. We're asking how much of this is in my signal or in my function. Let's talk about frequency, because this is pretty important to everything that we're talking about here. So if I have, let's use sine here. So first off, our function is a sum of a bunch of things that look like this. This is, every one of the c's is just a constant. It's a constant number, it doesn't change anything. The only thing that's changing is the t. As we change the t in here, it changes the t here. Each one of these looks like this for a different value of n, and each one of these is this thing, which we know that if f is a real thing, is a real valued function, we could rearrange these and get all of these c's to be real numbers, a and b, etc. But let's just take one of these. Let's just take sine, for instance, and think about what's in here. Before we look at that, let's just think about if I had this right here, sine of 2 pi t. And I want to know what is the frequency of that thing right there, of that function. Where t, we're going to assume now, it doesn't need to be in the general case, but just for right now, let's think about that t is in units of seconds. Well, if you have 2 pi t, then when you plug in a 1 in here for t, you get a 2 pi, which means that in the time that t has gone from 0 up to 1, it's made one full cycle. So you would have one cycle per 1 second if it's 2 pi t. Right? Makes sense? This review of trig here. Now if I multiply 2 by some number, let's say 2, then what we've done here is we've gone 2 full cycles in 1 second, right? Because when I plug in a 1, I get 4 pi, right? So as t goes from 0 up to 1, it's gone through 2 full cycles in 1 second. So this would be 2 hertz, or 2 cycles per second. So the frequency of this function would be 2. And indeed, whatever number I plug in here, let's call it, how about big capital N, whatever that happens to be, it's going to make n full cycles in 1 second. So this right here, whatever that is the frequency. I'm going to do FQ for frequency, okay? So looking at the way these are written, okay? The way these are, that we have them written right now, sine of pi n over L times t, if I could rewrite that as a 2 pi times something, then whatever that something is itself the frequency. But I don't have a 2 pi, I only have a 1 pi. It'd be nice if I could multiply it by 2, but I can't do that without changing it unless I multiply the top and the bottom of this fraction by 2. Now I have not changed it, right? This is exactly the same thing as this, right? Because the 2's cancel, etc., etc. But now this lets me pull that 2 pi out. I could rewrite that as 2 pi times what's left over, n over 2l. n over 2l, like that. And now we can see that this n over 2l in this expression here is the frequency. Right? So this thing will make n over 2l cycles every 1 second. Right? Cycles per second is frequency there. Okay? And so let's just go ahead and do this. I'm just going to rewrite this thing with a 2 here and a 2 here. I've not changed anything by putting a 2 in the numerator and in the denominator. And if I do that here and here, okay, and I can do that up here as well. In fact, I could go 2 here and a 2 here. Make this a little bit bigger, 2 here and a 2 here. And I have not changed anything. Everything that I have there is exactly what I had written up before, right? Okay, and so I want to keep this here. Let's kind of rearrange this stuff a little bit. I want to rewrite this so that it's easier to see. And as a matter of fact, this is really ugly the way I've written it. I'm going to rewrite it as how about 2 pi, and then I'll group the frequency part together like that. Okay, so that's what I'm going to do with all of these. For right now, let's just suppose that our original f is real. In which case, each one of these can be rearranged and blah, 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 to give us this right here, okay? Where an is some constant and bn is some constant, okay? And everything I'm about to say works just fine if it is complex, if it does have imaginary values as well, but we're just gonna take this special case here. Okay, so what this says here, what this says is that we can decompose my signal, f, I'm going to call it a signal, it's a function, but we're going to call it a signal. We can decompose f into sines and cosines, right? And so imagine that this is my f, defined on some interval from negative L to L, and every one of these is just some frequency, right? Like we have some frequency, n over 2 pi L, so what that is some cosine here. Right, there's your cosine for some frequency, n over 2 pi L, right? And we also have a sine here that has another one. And depending on what these numbers are, that affects the amplitude, right? If an is a small number, it's real small like that. If bn is a big number, then it's bigger, right? It's the same frequency, but bigger. Whatever it happens to be, that's how it works out. Then you take all of those, add them up, right? We add up all of those frequencies and we get our actual signal, our original f. Okay? So really what we're looking at here is what these things tell us, what these coefficients, indeed each one of these coefficients tells us is how much of each frequency is my original signal composed of. So you give me any n, and I could tell you how much, right, of sine of that is. And what I want to do here is, since this is dependent on n, I hate having that fq there, let's give this frequency a new name. We'll say that the frequency is s, and it's dependent on n, so s sub n is the frequency here. So, if I want to know how much, now let's make this concrete. Let's say in this case L is 1. So this signal or function is defined from -1 up to 1. And I want to ask how much of, I don't know, how much of 20 hertz is in there? How much of a 20 hertz frequency? So we have, and that kind of looks like what I've drawn here. Maybe we'll pretend that goes back and forth 20 times, right? How much 20 hertz is in this signal right there? Well, what I'm asking is, for what value of n do I have for this? What value of n would that be? Well, if L is 1, right, if we're assuming in this case, multiply across here, that's 2 times 1 is just 2. Multiply across and we have 40, okay? So when n is equal to 40, I plug in a 40 there and everything, and then I could do this right here and find out what that coefficient is. Or as you know, we have different ones for when it's a and b in, but like I'm saying, it's all the same thing. It's much easier to just think about it this way. Anyway, and okay, then I can find out how much 20 hertz do you have. That, well, there's that much of it in there. We figure that out and say, okay, C is this. That's how much 20 hertz is in there. That's cool. Okay, but what about if I wanted to know how much 1 hertz is in there? Okay, well, 1 equals n over 2, L is 1. So 2 equals n. I guess when n is 2, we'll find out how much 1 hertz is in there. But what if my actual signal was composed of something with a really long frequency? Like maybe the way that I generated this signal was I said, okay, f, oops, I'm going to need to use this. Maybe f is actually, maybe it's like cosine 2 pi times 0.02 t plus 3 sine 2 pi times 0.001 t, and that's how I generated this signal, right? Well, let's say, well, how much of 0.02 is in there? 0.02 is n over 2 times 1. Multiply the 2 up there, we'd have 0.04 equals n, but n can only be integers. So I wouldn't have access to that frequency. So this, I wouldn't be able to actually recover this. Another way of looking at this is, let's just think of all of the frequencies that we do have access to. If n goes from 0, and in the real case, remember how this works out, it's the sum as n goes from 0 up to infinity. That's how it worked out when we rearranged everything, etc. And if you're trying to figure out what is this thing composed of, well, the actual frequencies that we would have, the set Sn would be, well, let's just see. We have n over 2 times 1, so that's n over 2. And so we'd have 0, well, the 0, 1 is, I guess, yeah, okay, we would have it, whatever. Then when we plug in a 1, we get out a 1/2, so we'd have 0.5 as a frequency. Plug in a 2, you'd get your 1. Plug in a 3, you'd have 3 over 2 is 1.5. And so on. 2.0, 2.5, 3.0, and so on. But again, what if the actual signal itself had a frequency that was like 2.13? You wouldn't have access to that, would you? So what could we do to get access to it? Well, one thing we could do is make L bigger. And let's think about this. What does that do if I made L bigger? Well, let's say I doubled L. So we're going to now define this guy from 2, or from -2 up to +2. We're going to say now, in the case where L is equal to 2, now we have that. And you might say, well, wait, whoa, but this thing's not defined there. Well, what you could do is just say, well, we'll just pretend it's 0 then, from there to there. Everywhere where it wasn't originally defined, we'll just pretend it's 0. Or maybe your function to begin with wasn't finite, and you were just looking at a small part of it, and maybe it actually did more stuff as time went on, and whatever. Well, now we're getting more of it this way. Either way you want to construct this, what we've just done now is we've made our possible frequencies bigger. Right? The frequencies that now we have access to. Now when L is equal to 2, we'll have n over 2 times 2 is n over 4. And so what frequencies will we have? Well, we'll have 0, and then 1 over 4, which is 0.25, 2 over 4, which is 0.5, then 0.75, 1.0, 1.25, 1.5, and so on. Now we're getting more frequencies that we can analyze here. Now, if we were looking for a frequency that was, say, 3.75, we'd be able to find the correct n to plug into here to find out how much of this is composed of, how much of these make up my original function. But, again, if I did this, I wouldn't be able to get my 2.13 that I was looking for. So what can you do? Well, we can make L even bigger, right? If we go from, say, 4, from -4 up to 4, Now when we plug this in, we have 2 over 4. We have n over 8. Is that right? Yeah, 8. And so now we have even more frequencies. I think 1 over 8 is like 0.12. Yeah, I'm not going to try that, right? And so on and so forth. In other words, what I'm saying here, now let's think about over here in frequency. Let's make a new axis. Let's call this the S axis. Let's say this is 0 right here. When we started off, when L was 1, we were able to get 0.5, 1, 1.5, 2, 2.5, and so on. That was when L equals 1. When L equals 2, we were able to get 0.25, 0.75, 1.25, 1.75, all of these guys there. Make it bigger and you'll get all of these little guys here. And you can imagine what's going to happen as L gets bigger and bigger. When L gets really, 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 really large, you could get arbitrarily close, right? You pick the frequency that you're looking for here, right? Like we said, 2.13 is the one that we're looking for. Well, keep making L bigger and bigger and bigger, and you'll be able to find one for that, right? And now, if we're not thinking about real numbers, negative frequencies actually do have a meaning here. When you're thinking negative frequency, what does that do? Well, up here in the complex case, it does actually make sense, but whatever. We'll just you can imagine what's going on here, right? Like, we were able to get infinitely many frequencies when L was 1, because n goes on forever, right? We got 0.5, we got 1, we got 1.5. It went on and on and on, and n goes up to infinity, right? So it goes forever. You have 100 billion, trillion, 10 to the 10 to the 10 to the 10, and so on and so forth, but you only got the whole numbers and the halves, right? The 0.5, the 1.5, etc. Make L bigger and you get even more. And as L goes to infinity, you could get every single possible frequency that you want when L gets arbitrarily large. So, that kind of sounds like a limit, doesn't it? Let L get arbitrarily large, and then any number you choose here for S, like how much of 2.13, that'll be there. In fact, if you want to know how much of pi is in there, well, if L is arbitrarily large, you can get arbitrarily close to pi, if you like. And we say in the limit, you could get all of them. Okay, so let's think about this for a second. Now, I only brought the real case up there just so we could think about this as something on a graph, right? Like I just had written up, right? Thinking about it as a real function. But now let's go back to this right here. This thing right here. Let's take a limit and see what happens. So we have Cn is equal to 1 over 2L, from negative L to L, of whatever my function was, times e to the negative I, 2 pi, n over 2L t. And what you might be tempted to do is say, okay, if you take a limit of this, we're going to take the limit as L goes to infinity. You might want to say, well, then this thing goes to 0, because no matter what n is, 2 pi L, when I take the limit of this as L goes to infinity, obviously this gets arbitrarily large and it goes to 0. So that destroys everything that we have. If that's 0, then e to the minus I 0 times t is just e to the 0 is just 1. And so then that thing goes away, and essentially you just have this type of thing. Oops, I never put a dt here. Okay, you have this type of thing, and your e is gone, blah, 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 blah. But what we're not considering is that n itself is going to infinity, right? And like I said, and this should be suggestive, right? In S, think about S as my n over 2L. Since the n's went up to infinity too, as I make L bigger, what we're doing is we're covering all of these numbers here. And so this is a really weird case where when you take the limit of something here, right, we get, what ends up happening is, well, what this does is it gives you the possibility of getting any real number for S. And so it depends on what n you chose. And there also it also has something to do with this 1 over 2L out here. And I'm not going to go into that. That takes some finesse to deal with here. But what we're going to do is say that since n, and this should make some sense, is that since n is going to infinity, as you do this, really all you're doing is just picking up all of the frequencies that are inside of here. And remember, that expression right there is the frequency that we're talking about. So now, depending on what n you chose, I'm going to put a little n right there. Actually, I don't really need to. We know that we're going to say that when you take the limit, you could get any single frequency here. You choose your favorite frequency, a 10 to the 10 to the 10, or 0.000001, you'll be able to find it when you take that limit. And whatever that is, we're just going to call it S. Okay? So what does this do? And again, this is totally hand wavy. We're not going to go into this. It has something to do with this bad boy right here too. That's why this thing isn't blowing up, or this thing isn't going down to 0. This guy comes in and they play some rolls, etc. And what happens is that this thing and this thing, in fact, I'm going to go ahead and over here bring him in right there. And think about it like that. Oops. Oops. There we go. That guy right there. That thing makes that guy go to S. And so L going to infinity means that this guy, the limits now are going from negative infinity up to infinity. And we have f of t. Now, this thing is e to the minus I, 2 pi. This could be any number you choose. Any number you like. Let's just call it S, and that's the frequency, times t dt. And so, this right here is what this thing is. This gives you the coefficient given whichever n you chose, and whichever n you chose determines this thing right here, right? The n that you choose here determines this. So, in other words, the frequency and the n are connected. The S is a function of n, or you could think of the n as a function of S. And so I'm going to think about this thing now, since we've rewritten this, as a function of S. C as a function of S, the frequency itself. You wanted 2.13 hertz. We could plug in a 2.13 right there. Right there. Do this, and what you'll get is the coefficient, the amount of 2.13 that's in this original signal. And this is an integral transform. Right? Here's your kernel right there. Remember, integral transform, you have some transform of a function, right? You have the integral from some a or some alpha to some beta of your function itself times your kernel. That's a function of two variables, s and t. dt. And what you get is a function of a new variable, we'll call it capital F, of your new variable s, right there. That's all this is. This is in particular, we call this the Fourier transform of your function. And what it gives you is the coefficient in this expansion if you take the limit, which gives you access to all of the frequencies right there. T e to the negative I 2 pi s t dt. That's the definition of the Fourier transform. And again, what it does is it takes some signal, and we usually think of t as being in time, and it gives you a function of frequency. And we say that you're going from the time domain, when it's written like this, into the frequency domain. Where now you have a new function where you give it the frequency, and it tells you how much of that frequency is in your original signal. And you can think about these as the coefficients of your Fourier series right there. So given some function f, the Fourier series can be thought of as a way of representing this function in terms of its coefficients, Cn. You give me any n, and I can tell you what the C is here, right? What coefficient to put in front of here to make this. And if you have all of those coefficients, right, then you have all the information to reconstruct your f. This is just another way of writing this thing. The Fourier transform is the same thing as this, only instead of being locked into a discrete number of frequencies, you have access to a continuous amount of them. Right? You have infinitely many frequencies you could get by plugging in your different values of n. Because n goes from negative infinity to infinity, you're going to have infinitely many of them. And each one of these dots represents what the value of that coefficient is. But when you take the transform, it's the same thing as this. The only difference is there's no limit to how many. So you get it with the Fourier series. It's a discrete number, or it's a discrete representation, whereas the Fourier transform gives you the continuous representation of the same function. Whereas you used to plug in time and get out some value here for f, now you plug in a frequency and you get out the coefficient that is in front of the sine and the cosine to make that frequency. The actual extra credit question says, given that the Fourier transform of a nice function f is given by this formula right here, show that the Fourier transform of its derivative is equal to 2 pi times I times z times the Fourier transform of the original. And again, nice function means any function for which this thing converges. You're not guaranteed to converge, and there's whole branches of mathematics devised to figuring out what types of functions does this converge for. When can we say that that converges? There's like a whole branch of math that goes into that. We're not going to get into that here, but there you go. Okay, what we want to do is try to show that this is true. Okay, so I'm going to start on the left-hand side and just use the definition. Okay, so Fourier transform of some function is defined as you just put whatever that function is right here and do this. Okay, so the Fourier transform of f from negative infinity to infinity of, now instead of f, it's just f prime. So f prime of z, let's use s since I have s right here, or no, what am I doing? T, and then we're using s here, e to the minus I 2 pi st dt. And we need to somehow change that into there. Well, you know, I think if we do integration by parts, right? Because the whole point is I know that I need this thing, that I could turn this thing into this thing, right? I need this to show up somewhere. So I'm going to do integration by parts. U equals, okay. So I'm not going to use this as my u, because if I did, I would have then du is f double prime. That's going to show up in there. That's not going to help me get to where I need to go. So I'm going to let my dv be the thing that's the derivative, so that my antiderivative of it is the original thing. Everything else is going to be the u. So that's e to the minus I 2 pi st dt, or sorry, no, the dt should have been here. Yeah. Okay. And so then when I take the derivative of this, du gives me, well, this is the derivative with respect to t, so e to the stuff is just e to the stuff when I take the derivative. Then I need to multiply by the derivative of the stuff, right? So whatever that stuff is, its derivative. Well, what is that stuff? It's negative I 2 pi st. Take the derivative of that with respect to t. All I have left is negative I 2 pi s. Now, right? Oh, yeah, I used a z in there. I should have had it like that. I'm sorry. So in the way I wrote it, I had it as f of z, and I had a z there. And then I put a z here to show that, well, here we're using s. So I'm going to put an s there. Then the derivative of this should just be minus, and I'm going to rewrite that as 2 pi is times the stuff. The original stuff, minus I 2 pi st, like that. Okay. All right, now, uv minus the integral of v du. U times v is going to be, and I'm going to write it like this, f of tv times u, e to the minus I 2 pi st, evaluated up at infinity, down at negative infinity, minus the integral from negative infinity to infinity of v du. V is the f of t. Du is minus 2 pi is e to the minus I 2 pi st dt, like that. Okay, this is just a constant, because as far as this integral is concerned, s is a constant. So he comes out. And that's a negative 2 pi is, like that. Integral from negative infinity to infinity. That's f of t e to the minus I 2 pi st dt, like that. Negative, negative makes out a positive. So I'm just going to go plus this right here. Plus that. Now the only problem we have is figuring this out, right? We're going from here to here, so let's go the limit as big N goes to positive infinity of this stuff, e to the minus I 2 pi st, minus limit as m goes to negative infinity of f of, oh, it should be m, n there, n, and m e to the minus I 2 pi s m, like that. That's terrible. That looks just terrible. Now, as you can see, this right here, this part, is 2 pi is times, by definition, the Fourier transform of f. So this is plus 2 pi I times s times the Fourier transform of the original function f, which is what we want to show just as long as this goes to 0 as n goes to infinity, and here as n goes to negative infinity. Now you might be tempted to say, wait, as n goes to infinity, e to the negative infinity, that goes, well, you might be tempted to do that. And then you'd say, well, negative, positive infinity, e to the negative infinity. I think that's, what would that be? Well, that's like e to the negative x, right? E to the negative x, and going to positive infinity, that should go to 0. Yeah, right? Yeah. Or you could think about it as e to the positive x. Here's e to the positive x. As you go to negative infinity, that goes to 0. So that's nice. But you'd be wrong, because that's not, if you think about what is this, e to the I stuff, this is e to the negative I stuff. That's the same thing as cosine stuff plus I sine stuff. And so going to infinity or negative infinity in either of those, he's never going to settle down. This is just a unit circle. There is no limit. He's just going to go around and around and around and around forever. So, what do we do? Well, this is where I messed up. And like I said, in the actual text of the thing is, like it was like 1 a.m. and I was like, I just need to write some stuff down. I didn't. What I meant to do was tell you the key here is that one of the, for this to be nice, one of the requirements for f to be nice is that in both cases, the limit as n goes to infinity of f of n has to go to 0. And the limit as m goes to negative infinity of f of negative m equals 0. Another way of saying that is that your f, it can do whatever it wants, but as time goes on, he's got to go down to 0. He can do whatever he wants over here, but as time goes on, he's got to go to 0. So the limit of your original f has to go to 0 in both cases. Another way that that works, and like I said, this works for any finite function, or a function, function defined on a finite domain. Like I said this back in, when I first introduced this in another lecture, is that you could take any finite function and it's going to work. And as long as it doesn't blow up or it's not crazy, any continuous function on any finite domain from negative L to L, it works because technically you could just say, well, beyond that, we'll just call it 0. And so as you go on, then yeah, the limit is 0 because we'll just extend it and call it 0 whenever you're beyond it, so that when you take the integral, as you go out that way, this guy goes to 0. As you go out that way, that guy goes to 0. Or they're both the other way around, right? So that was what I messed up, and I'm sorry, it was after 1 a.m. when I was writing this down, and I meant to say part of it being nice. This isn't the only thing, but this is necessary. You have to have it so that your original f goes to 0 as you go to negative and positive infinity. It has to be that way. And since that's the case, e to that stuff is just rolling around the unit circle forever, but that guy's going to 0. So this goes to 0 times e to the I theta. So that doesn't matter. That goes to 0. This goes to 0 times e to the I phi, who's rolling around the unit circle forever. It doesn't matter because that guy goes to 0, so this entire thing goes to 0. And I am so sorry. I hope you didn't rack your brain trying to figure that stuff out. That's what happens. That's part of that function being nice. It has to go to 0 as you go to infinity. Otherwise, you can't do it. Or, if it's a finite function, you could just redefine it to be 0 everywhere that it's not defined, or defined on a finite domain. So you're good to go either way. And yes, indeed, that's what we wanted to show, given that, I'm sorry, these do go to 0 no matter what. Again, 1 a.m. when I was writing that, sorry. So there you go, that's what we wanted to show. the Fourier transform of a derivative of a function is the same thing as a Fourier transform of the original function times 2 times pi times I times s. Part B says use your result from part A to show this, that the Fourier transform of the nth derivative of f is equal to the Fourier transform of the original function multiplied by 2 pi is raised to the nth power. And I mean, you could do a full-on induction proof. That's not what I'm looking for. Really, I would just do this. I would say, well, hold up. From the first thing, part A gives us that this is equal to 2 pi is times the Fourier transform of f to the one less than that, right? One derivative higher than that, right? Because who's to say that f wasn't g prime to begin with? In which case, f prime is g double prime, right? And so then this is already a derivative, you know what I'm saying, right? Blah, 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 blah. So one derivative less than this would be n minus 1. Okay. But we know that this is the same thing. This, by this again, it is one derivative less times, so 2 pi is times f, but then again, one derivative less, n minus 2. Yeah? But then the 2 pi is the same thing as that 2 pi is, so how about I just rewrite this like this, 2 pi is squared. Like that. But if that's the case, okay, we have a 2 pi is squared. This thing, again, is 2 pi is times a Fourier transform of the n minus 3. Okay? But that is the same thing as 2 pi is squared. That's just a 2 pi is to the third. And we could say, okay, then you get one of them when it's n minus 1, two of them when it's n minus 2, three of them when it's n minus 3. So I'm not going to do a formal proof. 2 pi is would be to the nth power when you have f n minus n, which is the 0th derivative. The n minus n is the 0th derivative, so that's just the original function. So that's 2 pi is to the nth power times the thing that we're looking for, the Fourier transform of the original function f. Super simple. I was not looking for, like, you know, the base case and the induction step, blah, 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 right? You can just do this. That's cool. And if you really want to, that would be good, and it would be good practice to do a formal induction proof on this, but it's unnecessary, right? In part C, I said, imagine, just imagine how this could help you with differential equations. This is just, and indeed, you could imagine, right, if you did have some differential equation, f triple prime minus 3f double prime plus whatever, I don't know, f equals 0, you could Fourier transform these guys, right? And say, well, the third derivative is just that to the third, 2 pi is to the third. Take a Fourier transform of this entire thing, right? And then you'd have the Fourier transform of your original f, minus 3. Fourier transform is a linear operator, so this works just fine. 2 pi is squared Fourier transform of f plus the Fourier transform of f equals 0, because the Fourier transform of 0 is 0. So you would have the Fourier transform of f, your original function, times 2 pi is cubed minus 3 2 pi is squared plus 1 equals 0. And This is just some number, by the way. It's not gonna, nothing crazy is going on. You could just call this z, if you like. And you have Fourier transform of the original function times some number z cubed minus 3z squared plus 1 equals 0, right? And you could imagine, and this is what I'm saying, just imagine, right? We did this with the Laplace transform. We turned a linear differential equation into something that you can solve, you know, an algebraic equation. And then you come and you take the inverse transform, etc., etc. That's one way of doing it. And the Fourier transform is so much more versatile than just doing things with differential equations. It's, like I said, like I've been hinting at, I've been calling the t time, and when t is time, then s is frequency, right? And I alluded to, you could take Beethoven's Ninth Symphony and, you know, express it this way in terms of its frequencies and stuff like that. This leads to all kinds of analysis, like audio analysis, things like that, on top of which there's multi-dimensional Fourier transforms, where you can think of, say, a picture. Here's a picture of me. That's what I look like. And you could think about this in 2 dimensions. Every pixel along this way is a function in the, let's call this x, and we'll call this y. Each pixel value, imagine a black and white picture where a black pixel is 0 and a white pixel is 1. Each one of these is a function of x, and it has some value here between, say, 0 and 1. Right? Ditto right here. Each one of these columns is some, I'm going to call this G, and we'll call this H. H. Each column here is a pixel, and its output value is some number between 0 and 1. And so you could say then every single point on here, given some x and given some y, can be thought of as some values, x and y, a pair of values, x and y, where x is some value between 0 and 1, and y is some value between 0 and 1. And this is a perfectly well-defined thing, and it's well-behaved as well. It is a nice function as far as the Fourier transform is concerned. It's also finite, right? You have a finite number of pixels. You go from your first pixel up to your nth pixel. You go from your first pixel up to your nth pixel. And so thinking about these as functions, they're defined on some domain. That's finite. You could draw a new bit here, call this L, call this negative L. You can center him a new axis here and define him from negative m up to positive m. And there's a 2-dimensional analog for this thing. And you could re-express this thing. You could take the Fourier transform of that function, the Fourier transform of that function, and what you get is now frequencies. You could think about them as frequencies, but they're visual frequencies. And what ends up happening with pictures, this is what's really cool, is that most of the frequencies end up really close to here. So we think about this thing is, we can think about it as the graph of a function, kind of like we did in the 2-dimensional case, or I'm sorry, the 1-dimensional case where we had something like this. Each one of these itself is something like that, this way and this way, right? Depending on how bright the signals are, etc., etc. And so each one of these things can be broken down into frequencies, etc., etc. And now these frequencies go from 1 up to whatever it is. It actually goes over the entire plane, but we're not going to worry about that. Because what ends up happening, and this is what's really cool, is that most of these frequencies are small. And there are very, very, very few frequencies that are very large. And so what this does is it takes a picture that's spread out over all of this and kind of condenses it into a few frequencies. And this is how image compression is done. On your computer, if you save a picture, there's different formats you could save it into which you could save it. And I think it's either PNG or JPEG, I forget which one, compresses the image. So when you have an image that's a full, like let's say 10 megabytes, because however many bytes you have, 10 megabytes, right, 10 million bytes, you can use a Fourier transform to say, you know what, most of these frequencies are like right here. So we're going to throw out like the 1 or the 2 that's out there and just save these right here. So instead of saving, like let's say we had, I don't know, this is 1,000 by 1,000 pixels. So a total of whatever 1,000 times 1,000 is. I guess that would be 1,000 with that many more zeros. So a million, so 1 megabyte. Let's just say, and let's say that each pixel is a byte. It's not. But let's just say that you have 1 megabyte. Well, when you take the Fourier transform of that thing, the information kind of condenses into a smaller space. You don't need as many pixels or bits of information to be able to do it. And so that's how they do image compression. That's one of the ways they do image compression, is they take the Fourier transform of a picture, it condenses it, and now we could throw out all of this information that's out there that we don't need, and we'll just save this much, which is a reduction of however much it is. Let's say we get down to 5,000 pixels. And so we've thrown away, it's probably going to be more, it's probably 50. Okay, so you go from 1 million pixels, a million bits of information, bytes, whatever, 1 million pieces of information, and you drop it down to 50,000 pieces of information. And that's how you save it on your computer. And then when you want to go, that's how it's represented in your computer. And then you go to open it up, what the computer's going to do is take the inverse Fourier transform and give you back your original picture. And you could tell when you do image compression, it gets slightly blurry here and there, but ultimately you could still tell, yeah, that's a picture of me, there's no doubt about it. That's just one of, like I said, this thing, it's so versatile. And it can be used in ways that you never would have imagined, especially like this whole time I've been saying it's like a signal, and think about Beethoven's Ninth Symphony. You could write that as, okay, cool, that's nice. It's also how you can do audio compression, by the way. Same exact thing here. When you take a Fourier transform of a signal, usually tends to compress the information. It's not so spread out. Because honestly, when, in Beethoven's Ninth Symphony, we can't hear anything above like 40,000 hertz anyway, right? So you could pretty much just get rid of all that stuff, and then when you take the inverse transform, you get something that's legible or discernible. So I could go on about this all day. This is just a good example of an integral transform, and that I had mentioned a Fourier series earlier in the class. I wanted you guys to see this because this is seriously one of the coolest things. There's so much you could do with it. I mean, image compression is one, example, audio compression, but not just compression, also differential equations, and that's, you go to Wikipedia, look up Fourier transform, and you'll see that it's used in everything. Anyway, I hope this has been fun. If you've made it this far, you're pretty hardcore. Yeah, so this has been great. Thanks for being my students. Love you guys. Bye.